for some of those sea level changes. There are some that are on order of hundreds of millions of years, 2 to 300 million years. These are long-term changes that are associated with tectonic cycles. We will see some of these today when we talk about major sequences in North America. There are some of these that are shorter interval but still long, 20 to 30 million years, 1 to 10 million years. All these that are from million to 200 million years are directly associated with plate configuration and plate interaction, rates of seafloor spreading, among other things. And then these are shorter sea level oscillations that are mostly climatic in nature. Most of these are associated with Milankovitch cycles, those changes in amount of solar radiation that our planet was receiving through time that reflect on global time climate. So these are much shorter. They last from 10,000 years to 40,000 years to maybe 100 to 400,000 years. These are, geologically speaking, much shorter time intervals. And these are actually what we will see preserved in those sedimentary beds. When you see bedded sedimentary rock, it usually reflects one of the three Milankovitch cycles. So it may be even that bedded chert that looks very thin represents some of Milankovitch cycle. 40,000 years, this thick, but that's it for chert. That's how long it takes to build enough of ooze to make. So short-term climate related Milankovitch cycles, long-term changes, tectonic plate rearrangement in their consequence. Geologist, I forgot his Louis Stoss, I believe. No, maybe. Doesn't matter. His last name is Stoss. In 1950s, proposed this idea that's still valid, that when we look at the rock sequence in North America, we can recognize 6 major pulses of sea level rise, deposition of sediments that will then be separated by sea level drop, and conformity that will separate those major packages of rocks. He named those sequences according to some of the Native American names that populated Midwest or central part of the United States. The Sauk sequence, you can see how all sequences show steady but slow sea level rise. So transgression takes place progressively but slowly. It's not sudden, it's not sudden jump in sea level. It is progressive. And then, as it started near the end of Precambrian, it peaked at the Cambrian, and then it ended by sudden drop in sea level. Then you are recording?
Yeah.
Thank you. When sea level suddenly dropped to mark major unconformity, whatever was deposited in that Sauk sea started become lithified, or many of the sediments didn't have chance to survive because sea level dropped and erosion started removing them, eroding some that could not fully turn into rocks. Then we have next sequence, rise in sea level, that's marked by so-called Tippecanoe sequence. Again, slow rise, fast drop, sometimes at the end of Silurian. Then the next sequence was called Kaskaskia, that finished at the end of Mississippian. Absaroka is one that spans last part of Paleozoic and early Mesozoic. Zuni started in Jurassic and ended near the end of Cretaceous, and one that happened in Cenozoic era. This is the basic principle of all transgression. All sequences have the same pattern of sedimentation in them. And that pattern So, each sequence represents rise in sea level and the position of sediments that will possibly have chance to get preserved in rock records, a certain package of sediments preserved in rock records. So, at the onset of sequence, sea level is low because each sequence is separated by major unconformity. Unconformity means the land is very broad. A lot of land, ocean surface is little lower because low sea level allows many continents to get exposed more than during high sea level. Is that easy to understand? Okay. So as sea level starts rising, we said it is progressively happening, moving on land, flooding it, generally slowly. It is the pattern of sea level rise that is not suddenly 100 meters. It is a meter per few hundred years. It's fast in geology, that's right? So as sea level rises, land is still very abundant. All continents are still big. There is a lot of weathering that takes place on land, and a lot of sediment that was brought from weathering on land was brought to the sea, and that sediment is clastic sediment. Is that right? The sand is the major type of sediment I will say sand because of abundance of weathering on land, a lot of streams that bring the weathered sediment into that shallow part of the sea that's next to the land that builds plenty of sand to it. As sea level keeps rising even more, there is a slight diminishing of weathering on land, but there is still plastic sediment that remains. What used to be sand is now depositing near the shore, but here, further away from the shore, we have fine silt and clay plastic sediment that's building on top of this sediment that was predominantly sand in early stages of deposition. And we can do a little bit more flooding and do little sand near the shore, but more and more fine sediment a little bit further offshore. When we reach the peak of transgression, there is so little land left. There is so little plastic sediment production. So the land becomes so isolated and low, like small low islands that have very few rivers, very few weather particles end up from them in the sea. This is ideal for deposition of growth of invertebrates that will eventually lead to deposition of limestone. So we have sand first, there is a silt, clay, or mud on top of it, and there is a limestone. At the peak of transgression, where there is so little mechanical weathering, and the only weathering is chemical, the ions that come to the sea are now utilized by invertebrates that combine those ions to make their frames like reefs or shells like clams, oysters, and other invertebrates that prosper in that clear, warm water without much sediment because there is not much input from the land. So the package of major sequences has the same pattern. Sandstone at the base, some mudstone in the middle, limestone at the top. Sometimes mudstone components may be missing, but the key two lithologies are sandstone at the base, limestone at the top. Since new regression will happen, what will be eroded carbonate rocks or limestones at the top of the sequence. So we always find unconformity cutting through the limestones. And we always find unconformity that is at the base of the sandstone. So sandstone is always first rock unit on top of unconformity. Limestone is always last unit before next unconformity slices it to left. Now there will be next series of sands on top of this that will resume new sequence deposition. So that's the beauty of this, that we recognize from Grand Canyon that shows this sandstone, mudstone, limestone package of the single major sequence that allowed that deposition. And as I said, those last long, 100 million years, 200 million years sometimes. So those are long episodes. And they are not continuous. The sea level that we are talking over 100 million years doesn't go straight line up. It goes up, slight decrease up, generally up, but with few shorter breaks of slight drop in that 100 million interval. So this same what I was drawing here, the unconformity on top of it, sandstone, then some shale in the middle or mudstone, and then limestone before next unconformity cuts it and makes new sequence. So there is a beautiful example in Grand Canyon, near the base of Grand Canyon. You see there's Precambrian schists underneath, and then first sandstone. On top of that Precambrian schist is Cambrian age appeared sandstone, which is part of the soft sequence, the first major sequence. It deposits, and then water gets progressively deeper, we get bright angel shale on top of it, and then at the peak of transgression, where there is little land exposed in North America, an almost entire continent becomes submerged in water. The only sedimentation was chemical precipitation of carbonates through the help of invertebrates that utilize it and then leave it in rock. I think this is it for the recording, and we will now